Now consider flow over flat plate and heat transfer between liquid and surface is taking place at constant, I can't say constant, uniform heat flux. Okay, so it means in this situation the Nusselt number NUX or local Nusselt number NUX is given as 0.453 into Reynolds number to the power 0.5 Prandtl to the power 1 by 3. When the flow is laminar. Okay, and local Nusselt number NUX is given as 0.0308 Reynolds number to the power 0.8 Prandtl to the power 1 by 3 if flow is turbulent. Okay, now consider the flow through pipes. Okay, if a flow or fluid is entering or flowing through a pipe, in this situation a flow is said to be laminar if Reynolds number is less than 2300. That is, flow is laminar, and if Reynolds number is greater than 2300, flow is said to be turbulent. Okay, so in this situation let us consider the first case. Okay, constant surface heat flux, that is, heat rate of heat transfer from liquid to surface or surface to liquid is constant. In that situation Nusselt number Nu, or we can say average Nusselt number Nu, is equal to Hd upon Ka, that is nothing but 4.36. This is a constant value. Okay, when the flow is laminar. Now if the flow is turbulent, okay, what can we say in this situation? We give the Nusselt number Nu is equal to Hd upon K is equal to 0.023 Prandtl to the power n Reynolds number to the power 0.8. Okay, where n is equal to 0.4 for heating of fluid and n is equal to 0.3 for cooling of fluid. Now consider the second situation in which the surface or solid surface or pipe surface is maintained at uniform temperature. Okay, in that situation Nusselt number Nu is given as Hd upon Ka is equal to 3.66 if the flow is laminar. Otherwise Nusselt number is given as 0.023 into Reynolds to the power 0.8 Prandtl to the power n. Okay, this is for turbulent. Okay, where n is equal to 0.4 for heating of fluid and n equal to 0.3 for cooling of fluid. Till now, whatever relationship we have discussed between Nusselt number and Reynolds and the Prandtl number is for forced convection only. So, for forced convection, if I generalize this, for forced convection, Nusselt number is a function of Reynolds number to the power m into Prandtl number to the power n. Okay, this is known as the power law. Okay, now what will happen if the heat transfer between solid and liquid is due to free convection? Let us consider free convection now. Free convection. Okay, and free convection is also known as natural convection. In natural convection, we study one more dimensionless number, which is Grashof number. Okay, and this is denoted by gr. So the Grashof number gr is given as g into beta ts minus t infinity l cube upon nu square, where g is the gravity or acceleration due to gravity, which is nothing but 9.81 meter per second square. Beta is the coefficient of volume expansion. It shows the rate of change of pressure with respect to temperature, and it is given as minus 1 upon rho del rho upon del T when pressure is constant. Okay, and Ts is a solid surface temperature. T infinity is the surrounding temperature or fluid temperature. Okay, nu is the kinematic viscosity of fluid. The second dimensionless number which is important is Rayleigh number. Rayleigh number and denoted by Ra. So the Rayleigh number is nothing but Grashof number into Prandtl number is known as the Rayleigh number. Okay, so in this portion I will give you some formulas or empirical formulas to calculate the Nusselt number. Okay, let us consider a geometry. Okay, let us say first one we are considering vertical plate. Okay, this is our vertical plate and this is kept at a temperature Ts. Okay, and its length is L. Then its characteristic length LC is nothing but L, and the Nusselt number Nu in this case is given as 0.825 plus 0.387 into Rayleigh to the power 1 by 6 upon 1 plus 0.492 upon Prandtl to the power 9 by 16 whole to the power 8 by 27. Okay. Now, if the plate is inclined at some angle, let us say the angle from the vertical it is making is theta. Okay. Then, and its length is L, then its characteristic length is also L, and we will use the vertical plate equation, okay, for the upper surface of cold plate and lower surface of hot plate, and we will replace G by G cos theta if theta is in 0 to 60 degree. Okay. The third condition is a horizontal plate. Okay, let us say this is my horizontal plate and its length is L. Okay, so for upper surface, let us say its temperature is Ts and surface is hotter than the surrounding. Okay, so the condition applicable for this is upper surface of hot plate, or we can say lower surface of cold plate. Okay, then its characteristic length is given by as upon p, where as is the surface area and p is the perimeter, and the Nusselt number is given as 0.54 into Rayleigh number to the power 1 by 4 if Rayleigh number is between 10 to the power 4 to 10 to the power 7, and Nusselt number is given as 0.54 Rayleigh number to the power 1 by 5 if Rayleigh number is between 10 to the power 7 to 10 to the power 11. Okay, now in the same horizontal plate condition, let us say this is a situation. If this is a horizontal surface and this is our plate, okay, and this is kept at temperature Ts, which is hotter than the surrounding. Okay, then for this surface, okay, we will use the formula Nusselt number is equal to 0.27 into Rayleigh to the power 1 by 4 for all the Rayleigh numbers. These things are important from the free convection point of view. Okay, so this relationship is applicable for a lower surface of a hot plate, or B upper surface of a cold plate. Okay, let us say this is a hot plate. I hope this is clear. So this is the end of convection portion. So in convection, they mainly ask questions based on these empirical formulas. So you need to remember all these formulas, especially for the forced convection. Free convection is not very important from the gate point of view. In the next topic, we will discuss the heat exchanger. How can we analyze a heat exchanger? How can we find out the size of a heat exchanger if we know how much heat we want to extract from a device?